Hi, this is Daniel Chen, and this is my Lab 7 on curving motion. So our problem is that there's a star orbiting a black hole of unknown mass. You can assume that the net force on the system is due solely to the gravitational force of the black hole, and our goal is to estimate the mass of the black hole. So the main result of this was that because the net force is equal to only the force of gravity, we can determine the mass of the black hole by using the formula to calculate gravitational force and plugging in values from our Python program. Alright, so here are the concepts that we're going to apply in order to solve this problem. So first off, it involves curving motion because the sun is moving in an orbit, which indicates that its momentum is continuously changing. And from the momentum principle, we can conclude that if an object is moving along a curved path, then it must be subject to a non-zero force. And here we have dp dt equals f net, and the change of momentum can be broken down into its parallel and perpendicular forces. Alright, so let's go ahead and take a look at the Python program. It's the exact same code that we wrote in lab last week, except that the star data file and inputs is a little bit different. Here are the initial conditions. The mass of the star is set at 1.989 e to the 30 kilograms. Delta T is a day in seconds. Here's where it loads the star data file, and from that it creates two arrays. One contains the x components, the other contains the y components. So from the arrays, it takes 2 points and continuously calculates v initial, v final, p initial, and p final. And from that information, we can calculate dp dt, and we set f net equal to dp dt. So this is where we calculate the parallel component of dp dt, which is just p hat times the magnitude of dp dt parallel. And again, we set f net parallel equal to dp dt parallel, and dp dt perpendicular is dp dt minus dp dt parallel. And finally, f net perpendicular is set to dp dt perpendicular. And this is the portion where we create arrows representing the magnitude of the forces in the f net direction, f net perpendicular direction, and the parallel direction. Okay, so let's go ahead and run the program. Here you can see the sun orbiting the black hole with the arrows representing the forces, and we'll get back to that later in a sec. But here I have the program print out the mass of the star, the position of the star, and the force of gravity. So if you take this information and plug it into the formula to calculate the force of gravity, then after putting in all the numbers and doing the math, we get that the mass of the black hole is 3.55 e to the 31st kilograms. Okay, so what does it mean? Well, if we go back into our Python program and look at it, we can see these arrows representing the magnitudes of the forces. The blue arrow represents the parallel force, red arrow represents the perpendicular force, and the black arrow represents the net force. So how exactly do these quantities relate to dp dt, dp dt parallel, and dp dt perpendicular? Well, these vectors are equal to each other, but they're not exactly the same thing. If you know the net force, then you know how much the momentum will change, and you can update the momentum. So it's better to say that the momentum change is caused by the net force. Alright, so what if we tried to find the mass of a different black hole that's at the same location as the original? Again, we can assume that the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. So this is actually impossible because the data that we're given is unchanged. So that means that our calculation will always result in the same answer, and we would not be able to find the mass of the new black hole. Alright, just to wrap things up, once again I calculated the mass of the black hole to be 3.55 e to the 31st kilograms, and this result was found by plugging in values from the Python program into the formula to calculate the gravitational force and solving for the mass of the black hole. Alright, thanks for watching my video.